Hello and thank you for joining. I'm MD Yusuf Harun, a PhD candidate at Rochester Institute of Technology. Today I'm excited to present our CoLLAs 2025 paper titled A Good Start Matters Enhancing Continual Learning with Data-Driven Weight Initialization. Continual learning systems must rapidly adapt to new concepts while preserving and leveraging prior knowledge. Typically, when new categories are introduced to a continually trained deep neural network, the classifier weights are randomly initialized. This leads to high initial training loss, also known as loss spikes, and instability. As a result, achieving good convergence and accuracy requires extended training, which increases computational cost. A key question we explore is how should we initialize the last layer classifier weights for new categories in continual learning? We analyze loss spikes in a class incremental learning setting. Here, a convex model pre-trained on ImageNet 1K incrementally learns 5 tasks, each containing 73 semantic categories from the Places 365 standard dataset. Each task runs for 1250 training iterations. We observe that random initialization causes consistent loss spikes across all tasks, which degrades new task accuracy. In contrast, data-driven initialization effectively mitigates these spikes and improves accuracy. TLDR. Inspired by neural collapse, we propose a least square based weight initialization method that aligns the classifier weights for new classes with their corresponding feature distribution. What is neural collapse? Let's first look at neural collapse, a phenomenon observed in well-trained classifiers. In this regime, class features collapse into tight clusters that align with a geometric structure called the simplex equiangular tight frame or ETF. We characterize neural collapse using four criteria: NC1 feature collapse, NC2 simplex ETF structure, NC3 self-duality, NC4 nearest class mean decision. We use these criteria to measure the extent of neural collapse. We build on the mean squared error loss decomposition proposed by Han, which shows that MSC trained deep networks naturally approximate a least square classifier. We begin by deriving the least square solution WLS for the classifier weights. Let W be the weight matrix and Z and Y be the feature and one hot label matrices. The MSC loss can be written as shown in equation 1. By taking the gradient of loss L with respect to W and setting it to 0 as shown in equation 2, we obtain the least square weight formulation in equation 3. This solution depends only on the feature statistic Z, making it ideal for weight initialization for new categories. By aligning initial weights with the data distribution, least square initialization enables faster and more scalable learning from the outset. We aim to study continual learning in an industry-relevant setting which involves a large-scale data stream with many object categories. To build such a data stream, we combine ImageNet 1K dataset with Places 365 standard dataset, creating a dataset of 3 million images and 1365 classes. We then split the Places 365 dataset into 5 disjoint tasks, each containing 73 non-overlapping classes, to simulate class incremental learning setting. While our focus is on replay-based methods, our weight initialization is method agnostic and can be integrated with any continual learning approach. We also evaluate methods like elastic weight consolidation and dark experience replay. To simulate real-world constraint, we fix the number of training iteration and limit storage with a fixed size replay buffer. This buffer follows a class balance sampling policy by storing an equal number of randomly selected samples per class. We evaluate models on new, old, and all tasks. We also report forward transfer and adaptation speed. Our comparisons include three methods: random initialization, class mean, and least square. We first assess how weight initialization affects adaptation to the first continual learning task, evaluating performance before any training begins. Here's what we find. Random initialization fails to achieve non-zero accuracy due to its lack of alignment with feature statistics. Least square initialization achieves the highest accuracy, followed by class mean. This highlights that data-driven initialization provides a strong foundation for rapid adaptation. Next, we measure how quickly each method adapts. On the first continual learning task over 3000 iteration, least square initialization reaches 95% of random initialization's peak accuracy with 7 times fewer iteration. This demonstrates that data-driven initialization leads to significantly faster learning. We now explore continual learning under a frozen backbone setup. Here the feature extractor remains unchanged, only the final classifier is trained. In this setting, least square initialization improves new task accuracy and overall performance improvement is significant. The training loss is also reduced due to least square initialization. It also speeds up learning, outperforming random initialization under all tested conditions. We also study continual learning under controlled plasticity settings. Inspired by prior work, we fine-tune the top layers using low-rank adaptation or LoRa while keeping the rest of the backbone frozen. During training, only the LoRa parameters are updated. Afterward, they are merged back into the backbone. The last layer classifier remains plastic. Under this setting, least square initialization again improves both new task and overall accuracy. While class mean performs reasonably well, it consistently lags behind least square. Loss is consistently lower with least square, confirming its benefit for efficient, scalable continual learning. Here we ask, does least square initialization work effectively across different continual learning algorithms? To evaluate this, we apply it to two common continual learning methods. Elastic weight consolidation or EWC, which is a parameter regularization method. Dark experience replay plus or DER plus, which is a rehearsal with distillation method approach. Under the control plasticity setup, least square consistently outperforms both random and class mean initialization. This demonstrates its robustness and broad applicability. While our main experiments used connext architecture for its modern design and strong performance, we also evaluated ResNet 18. Using a frozen backbone setup, we incrementally train an ImageNet 1K pre-trained ResNet 18 model on 5 class incremental learning tasks from Places 365 standard dataset. Across all criteria, least square again outperforms random and class mean baselines, confirming its effectiveness across architectures. To summarize, least square initialization improves large-scale continual learning. It mitigates loss spikes, speeds up adaptation, and enhances overall performance. It's easy to integrate, no changes to pre-trained networks or added memory are required. For future work, it would be interesting to explore alternative loss functions that address the limitation of cross-entropy loss. We primarily focus on image classification tasks. Future work should study the efficacy of our method in other tasks and modalities. We thank the US National Science Foundation for supporting our research. Thank you for watching. You can find the full paper at the following link. We welcome your questions and feedback.